Hey folks, Ms. Gosling here with another example video on solving impulse and momentum problems. In this video, we are going to be discussing the method that I suggest for solving collision problems. Now, as we discussed in class, there are multiple kinds of collisions. This is going to just look at one kind of collision, but this method is appropriate for any collision problem that you might have to solve. So with that being said, let's go ahead and get started. In our problem, we have a 10-kilogram medicine ball, which is thrown at a velocity of 15 meters per second to a 50-kilogram skater who is at rest on ice. The skater catches the ball and subsequently slides with the ball across the ice. What is the final velocity of the skater and the ball? Now, to start off, I'm going to go ahead and just identify the kind of collision that this is. So we know that our skater and our ball are moving together. They're sliding together after the collision happens, which means that this is a perfectly inelastic collision. So I'm going to go ahead and write that down. And I know this because the ball and the skater are moving together at the end of my story. So now let's go ahead into solving the problem. And what I know is that the law of conservation of momentum says that my final momentum and my initial momentum will be the same. So no momentum is lost during the collision. And to go ahead and do that, and to solve this problem, I'm going to draw a before picture and I'm going to draw an after picture. So let's go ahead and draw those in. So before, I have my 10-kilogram medicine ball. I'm going to go ahead and draw the mass outside of it because I don't have space in it. And it's being thrown at a velocity of 15 meters per second at a 50-kilogram skater. So here is my skater. And she is 50 kilograms. And I also know that her initial velocity is 0 meters per second. And I know that from this bit here where she is described as being at rest. So that is going to be my complete before picture. And I'm going to go ahead and draw a line down the middle of the page and draw my after picture. So after, I have my skater and my medicine ball. So skater and medicine ball. And my skater is still 50 kilograms. My medicine ball is still 10 kilograms. And they are moving together with a final velocity that we are trying to find. So that, again, is our unknown in the problem. And so you guys, you might notice this is a little bit different from our traditional guess method because I have to focus not only on one part of the situation, but on the before and the after parts of our problem. So you can turn this into a guess method problem if you want. It's a little easier, I find, to do before and after instead. So let's go on to the next part of this, and that is going to be summing up our momentum before and after. So I'm going to go ahead and I'm going to say the momentum of the ball before plus the momentum of the skater before is equal to, and so this line down the middle of my page is actually going to be my equal sign because, again, my momentum before, my momentum after are the same. And that's going to equal the momentum of the ball after plus the momentum of the skater after. And I'm going to use the little F here to show final versus initial. Now I can go ahead and expand out my equation a little more. So the mass of the ball times the velocity of the ball plus the mass of the skater times the initial velocity of the skater is equal to the mass of the ball times the final velocity of our ball skater system, because remember they're moving together after, plus the mass of the skater times, again, that same final velocity that they share. So I'm going to do one last thing before I start putting in numbers. And what that's going to be is I'm going to go ahead and combine, so simplify a little bit, the right side of my equation by factoring out that v final. So what I'll get is that the mass of the ball times the velocity of the ball plus the mass of the skater times the velocity of the skater initially is equal to the mass of the ball plus the mass of the skater times their same final velocity. Now, I can only do this in a completely inelastic collision, a perfectly inelastic collision, because this is going to be the only situation where my two items are stuck together at the end of my story. So just keep that in mind when you are solving these problems. And now, I am ready to plug in numbers. So the mass of the ball is 10 kilograms. Its initial velocity is 15 meters per second, plus the mass of the skater, which is 50 kilograms, times the initial velocity of the skater, which is 0 meters per second. And that is going to equal the mass of the ball, which is, again, 10 kilograms, plus the mass of the skater, which is 50 kilograms, times their final velocity. So let's go ahead, cross off that 50 times 0, because, of course, anything times 0 is 0. We know that the left side of our equation now, the total initial momentum of our system, is 150 kilograms meters per second, and that is going to equal 60 times my final velocity. So now I have to finish and solve for my final velocity. I'm going to go ahead, divide both sides by 60. And what I will get is that the final velocity of the ball in the skater is 2.5 meters per second. So, as always, the last thing that I want you to do is do your sanity. So, before, we have a 10 kilogram medicine ball, so a smaller mass, moving at a larger velocity. Small mass, I'm going to go ahead and do this in a new color. So we have a small mass, so this is our before situation. Small mass plus big velocity. So little mass, big velocity. After, we have a big mass and a smaller velocity. So equals big M times little v. And so this should balance out, right? So as your mass increases, your velocity will decrease in order to ensure that your total momentum is the same. You can also always go back and check just to make sure that your answer works by plugging that 2.5 meters per second back into your equation and making sure that it's equal to 150. I'm going to let you do that on your own if you would like, but as of this point, you should have everything you need to solve problems. Just remember, you cannot always factor out your final velocity. Also, you may need to think about, for example, a superelastic collision problem where an object is initially at rest, something is thrown, and that changes the velocity. So just make sure you're being very, very thoughtful about what goes in your before column and what goes in your after column. So think about what's the beginning and what's the end of my story. Okay, guys, you have everything you need to solve. Go ahead, give it a shot. As always, I'm available by email if you have any questions. Happy solving!